So let's start with the von Laue semi-empirical approach in X-rays. So, um, so as we know that first let me draw the diagram. So this is a crystal here. So this is a crystal of diameter d basically. So this is a crystal, and as we know, the incident plane wave has an electric field. Um, so this is the direction of the incident plane wave, and this is the direction of the electric field, which is perpendicular to the direction of the propagation of waves. So this is basically the direction of wave vector ki. So the expression for the incident plane wave, which has an electric field, is given by this equation, that is ei is equal to e naught ei ki r minus omega t. So in this case, we can see that electric field is perpendicular to this direction of propagation because electromagnetic waves in vacuum are transverse waves so this is the diffracted waves, and here we have detector. So this is detector here, which measures the diffracted waves. So at the detector we have the scattered wave vector, that is ks. So by the first hypothesis, that is by elastic scattering, the frequency omega doesn't change. So we will not consider this e power minus I omega t term in this expression. So we are not going to consider this expression in the above equation. So so suppose we have atoms here. This is the atom with electrons. Okay, that is okay. Now we have these plane waves. Which hit this atom, or which interact with the electrons of this atom, and after interaction, this plane wave put the atom in oscillation mode. So this oscillation generates an oscillating dipole. So this oscillating dipole radiates at large. This radiates at large distance. So we can tell of this oscillation, the radiating waves are at large distance or almost spherical waves. So the interference between the spherical waves emitted by many atoms can be constructive or destructive. So in particular direction, it gives high diffraction intensity, that is the diffraction peaks, which we have already covered in the previous lecture. So let's understand this phenomenon with the help of some equations. Now, um, we know that the incident wave vector is given by this expression, that is 2 pi by lambda. Now let's consider one atom. Let's consider first one origin. So this is the origin. So this is origin O, and let's consider an atom at um, this point. Let's consider one atom here at this point from the origin. So this is the our atom. This is our atom at position of Bravais, that is n vector from the origin, given by n vector. So n vector is one of the Bravais lattice. So n vector here is the Bravais lattice. So there are other atoms also at other lattice position. So for this semi-empirical approach, we will consider a simple crystal, that is we have one atom at each lattice point and we have no basis. So the atom when got, now let have let us have some plane waves arriving. So this is the plane waves with a direction, plane wave vector direction ki in this direction, and electric field is perpendicular to the propagation of the direction of the wave. So here we write EI is equal to E naught EIKR. We have ignored the frequency because by elastic scattering the frequency doesn't change, so we have ignored the frequency term here. Okay, so these are the plane waves. So these are the plane waves. So when this atom get hit by these plane waves, these arriving plane waves, they generate spherical waves which go outside in any direction. Suppose let's extend this direction of propagation to this point. Okay. Now when plane wave hits the atom, it generates spherical waves in this fashion. So imagine that we have a detector in this position. Now we are going to put detector here. Now we have put detector at this point. So this is a detector. So let's assume the distance between the detector and the origin as let me give this as r vector. That is the distance between the detector and the origin is r vector here from the origin. So the generated waves comes to the detector. So the other waves generated by other atoms also arrive at the detector. So by construction, the distance between the atom and the detector is given by this vector, that is r minus n vector. So let's write this scattered wave amplitude. This is phi angle. This is phi angle. This is angle phi. Now let's write the scattered wave amplitude equation at the detector. That is, we want to write what is the amplitude of the electric field generated by the atom, that is the spherical wave at the position of detector, which is given by this expression, that is E naught ei k dot ki dot vector and vector. So this is the instant wave in the position of atom. So this is the incident wave in the position of atom. So like we say that the amplitude of the scattered wave will be proportional to the incident wave. So if you send a strong wave, we will have a strong wave at the detector. That is, we will have a strong intensity of waves arriving at the detector after scattering. So, and vice versa. And let's complete this expression by multiplying this expression with the amplitude, that is the scattering amplitude. So to multiplying with this scattering amplitude, our expression becomes in this way: ki dot n vector. This is amplitude. So we call this as scattering amplitude. So what is scattering amplitude? So scattering amplitude is the capacity of the oscillating atom to scatter the electromagnetic wave. So let me write. It is the capacity. It is the capacity of oscillating atom to scatter the electromagnetic wave. So basically, the scattering amplitude shows how strong is the spherical wave generated by this atom. We don't care how much it is, we just understand its value, which depends on the type of atom. For example, for carbon and silicon, we will have different value of scattering amplitude. Now, what is the typical expression for a spherical wave? So a typical expression for a spherical wave for a spherical wave is given by EIKR minus E minus I omega t. Sorry, this is multiplication. This is omega divided by R. So this is the typical expression for the spherical wave. Now let's complete our full expression. So multiplying this term, which is the expression for a spherical wave, in the above expression which we have obtained. So we are going to get the expression as E naught dot EIKN dot A multiplied by the expression of the spherical wavefront, that is KR minus n vector divided by R minus n vector, that is, which is the distance between the detector and the atom. Here this k is the modulus of the wave vector. Which wave vector? this scattered wave vector. Scattered wave vector, which is in the direction of r, this direction, which you are observing from this diagram. Now remember that we have elastic scattering. So this scattered wave vector becomes, the modulus of these scattered wave vectors becomes equal to the modulus of the incident wave vector, which is equal to k, due to the elastic scattering hypothesis. Elastic scattering hypothesis. So why we have used scattered wave vector in the direction of r, not from r minus n, as the spherical wave originate from the atom? Because here the k vector is different from each atom, so the direction of r minus n vector, so if the position of the atom changes, then the value of k in the direction of let me here. So here ks is in this direction, ks is in the direction, and ki is in the direction. So the main question is that why ks is in the direction of r vector, not from this r minus n vector. So I'm going to repeat again, because k vector is different for each atom in the direction of r minus n vector. So we generally use far field approximation. So since we are in far field, we must imagine the position of detector is very far. So basically r vector and this r vector and this r minus n vector are almost parallel. So in far field approximation, we don't see the difference between the direction along r vector and r minus n vector. So the scattered wave vector from all the atoms are same. So let's write the expression of this scattered wave vector. So scattered wave vector is given by this expression. So this is the modulus of k. This is the modulus of k. This is k modulus of k along the displacement of r, along the displacement of r. So we can write it as this whole expression as k in this fashion. So here u vector r is the unit vector. So this thing is ur. So ur is the unit vector along our direction. So let's also define angle of scattering defined by phi. That is this angle. This is the scattering angle. Now let's define the expression for this scattering angle. So by construction we can observe that suppose this is the arriving that is the incident wave vector, and this is the scattered wave vector ks, and we are going to extend this here. So this is basically scattering angle phi. Now let's move this ki to here. Now we are going to get the expression as like the diagram as something like this. This is incident wave vector, and this is scattered wave vector, and this is the difference between ks and ki is represented by this thing given by q equal to ks minus ki. So the difference between ks and ki is very important quantity which we will use in our calculation, upcoming calculation. So this is phi, that is the scattering angle. So this q vector is known as scattering wave vector. Scattering wave vector. So q is very important quantity in diffraction. So basically it is the exchanged wave vector of the crystal. That is, it is the difference between the input wave vector and the output wave vector. Now let's use the our hypothesis which we have studied in the previous lecture, that is far field approximation. So we are going to subject the far field approximation to this distance, that is r minus n vector. So which is the distance between the detector and the oscillating atom. So by far field approximation we can write this as this format. So after solving we are going to get something like this expression. Now take r common. So we are going to get this expression. We are going to neglect this expression. This is neglected. So because r is very greater than 1, so we can consider it as 0. Because position of detector is much more than the position of atom with respect to origin, so we are neglecting this term. So here we can write, we know by basic mathematics, so we can approximate this expression in the form of 1 plus x by 2. So we can approximate this term in this format, that is 1 minus n. If this expression is tending towards 0. Now let's multiply by k. So we are going to get k dot r minus n modulus. So we are going to take expression in this fashion. So we know that unit vector, so we can write the expression as kr minus kur dot n vector. Here ur is the unit vector. So we know that k multiplied by unit vector is the scattered vector, scattered wave vector. So here kr minus ks dot n vector. So now let's put these values into the main expression, that is so basically this is our main expression. This is the main expression. We are going to put the value of r minus n vector in this expression. So after putting the value in this expression, we are going to get so the amplitude of the scattered wave vector, scattered wave or the spherical wave, is given by a naught, e naught. Sorry, this is a e I k I r vector multiplied by e minus I k s n dot n vector divided by r. So this is the scattered amplitude by one atom. So this is the overall expression is for scattered amplitude by one atom. Now let's write the total amplitude of the detector. So the total amplitude at the detector is given by this expression, sum over all atoms a e naught e I k I n vector multiplied by e minus I k s n vector dot e I k r by r plus the incident wave, that is e naught e I k I r. So why we are considering the so why incident wave is added to this expression? Because incident wave is always there, it doesn't disappear. We have spherical waves coming to the detector, but also these plane waves can continuously hit the detector, like in this fashion. So suppose this is our atom, and here is our detector, and this plane waves, deriving plane waves, also hits the atom also, and also simultaneously hits the detector here. So it also goes to the detector. So we also add the instant wave vector expression to our total amplitude at the detector. But now we will use our last hypothesis, that is small angle. So the plane wave is not infinite, it is limited. That is so we will go as a narrow region. So there is a less chance that there is a narrow plane waves which will hit the detector. So we will neglect this term. So we are not going to consider this term. So our so let's simplify the above equation by taking out all thing which doesn't depend on n vector, that is the Bravais lattice. So the expression becomes something like this: e naught a e I k r divided by r summation over all sum over all atoms e minus I q n. Now the situation is getting interesting. So this expression here, this expression, so this expression here is the modulator. This is the modulator. Here we have the physics of interference. So this describes the interference between all the atoms. This term describes the physics of interference between all atoms. So if we analyze this, we will see in which direction we have the constructive interference, that is peak of diffraction or not. So all the problem of understanding of diffraction is to calculate this quantity. So this quantity itself. So it also gives the density at different angles. Now let's see how the scattered scattering wave vector, that is q vector, depends on angles. So what is the q modulus? Yeah, so this is our incident wave vector ki. This is our scattered wave vector ks, and this is the difference between ks and ki, that is q vector. Now if we take perpendicular to the q vector in this fashion, this is the perpendicular drawn to the q vector, this is phi. So here the q is the 2 times of this green shaded portion. So this is the green shaded portion. So we can write the modulus of q as 2k sine phi by 2. So we can write 4 pi by lambda sine phi by 2. So now let's in the next lecture we will be moving to the case of particle nature, particles. So suppose when the crystal is getting hit by the particles, that is either electrons or neutrons. So in this lecture, so in order to summarize, in this lecture we have studied the von Laue semi-empirical approach. So that is how to study the diffraction condition when the crystal is hit by the X-ray waves. So in the next lecture we are going to study about the diffraction condition for the particles, that is electrons and neutrons. So for now, thank you.